Welcome to the Deep Dive. Our mission today is a deep exploration into the heart of magnetism, specifically focusing on Chapter 37, Magnetic Materials, from the Feynman Lectures on Physics, Vol.2. We've taken this dense academic source and distilled it conceptually for you.
Yeah, this chapter is really something. It brilliantly connects the tiny quantum world of electrons, their behavior, directly to why big things like iron or nickel act as magnets.
All right.
We're basically going to walk you through where ferromagnetism actually comes from. It's maybe not what you first expect, and it explains why your refrigerator magnets stick. And we'll try to do it without getting lost in the heavy math.
Okay, let's unpack this then. We're aiming for a clear, step-by-step feel for the physical ideas. Now, most people, when they think magnetism, they probably picture little currents, maybe electrons zipping around an atom. But this chapter says, for ferromagnets anyway, that's not really the main driver. So what is the true source?
Okay, so the real source, the dominant one, is an intrinsic property of the electron itself. It's called spin.
Spin, not orbital motion.
Exactly. You can think of the electron as having this built-in angular momentum, and tied to that, a built-in magnetic moment. It's just part of being an electron.
Sure.
And it's quantum. So its orientation is restricted basically up or down relative to some axis. And the crucial point here is that the magnetic effect from the spin just dwarfs any effect from the electron orbiting the nucleus.
Okay, I get that for one electron, but the real puzzle is getting all the electrons in a solid chunk of iron to line up.
Right.
If you just had two tiny bar magnets, they wouldn't naturally all point the same way if you pack them together. They'd probably flip and repel or arrange head to tail.
That's a great point.
So what's the force making billions of these electron spins in neighboring atoms all snap into perfect alignment? It doesn't sound like a normal magnetic interaction.
And it isn't. That's maybe the most amazing part. The force doing this isn't magnetic at all. It's a purely quantum mechanical effect. We call it the exchange force, or sometimes exchange coupling.
Exchange force. Okay, that sounds subtle. How does that work? If it's not magnetism pushing them, what is it?
Well, it comes down to the quantum exclusion principle, the rule that two electrons can't be in the exact same state.
Ah, Pauli exclusion.
Right. When electrons are close neighbors, their quantum wave functions overlap, and this interaction creates an energy difference depending on whether their spins are parallel or pointing opposite ways, antiparallel. The source material explains this really nicely without heavy equations. It shows an electron's energy depends not just on an external field, if there is one, but also on the average magnetization of its neighbors.
So the neighbors affect its energy state.
Precisely. And there's this constant, lambda, which captures the strength of this exchange coupling. Now, in materials like iron, lambda is positive. That means the system has the lowest possible energy when the spins are lined up parallel.
It's like they prefer to be parallel, energetically speaking.
Exactly. It's an energy-based preference for alignment driven by this quantum exchange effect.
Okay, so because parallel is the lowest energy state, the whole material just spontaneously lines up. That leads to what the chapter calls spontaneous magnetization, MZAP.
That's it. The material becomes strongly magnetic all by itself, no external field needed.
Wow.
And this alignment is strongest near absolute zero temperature. But as you heat the material up, the thermal vibrations start to mess with the alignment.
Things get jiggled around.
Yeah, exactly. The magnetization gets weaker and weaker until, boom, it vanishes completely above a certain critical temperature. That's the Curie temperature together.
And the way it vanishes, is that simple to predict?
Not at all. That's another key point. Classical physics predicts a sort of gentle fading away. But that's not what happened.
No.
No, the actual experimental curve, how magnetization drops off with temperature, it's quite specific. And you only get that curve if you use the full quantum mechanical picture. It's a real triumph for quantum theory, actually. It matches iron, nickel, cobalt perfectly.
Okay, thinking about heat again. This spontaneous alignment, this ordering, must have some effect on the material's energy content, right?
Oh.
What happens thermodynamically near that Curie temperature?
Good question. If you look at the material's specific heat capacity, CV hours, which is how much energy it takes to raise its temperature. Well, as you approach material from below, the specific heat shows this really sharp spike.
A peak. Why?
It signals the complex magnetic ordering transition. The low Curie-like energy is stored in maintaining that alignment. As you heat it towards $, the system absorbs energy to break that order. Right at the water, the order collapses, and there's this sudden change in how the material handles heat energy. That peak is like a fingerprint of ferromagnetism ending.
Interesting. Now, the chapter also dives into a really neat experiment to prove this whole thing really is about spin? The gyromagnetic ratio measurement. What did that tell us?
Ah, yes, that's a classic. It's quite clever. See, when you magnetize a bar of iron, you're flipping all those electron spins. But electron spin isn't just magnetism. It's also angular momentum, like a tiny gyroscope. So if you change the direction of all those spins, you must be changing the total angular momentum of the entire iron bar.
The whole bar should slightly twist or resist twisting.
Something like that. You can measure the change in magnetic moment and the resulting change in angular momentum. The ratio between these two tells you what's causing the magnetism.
And what did the ratio turn out to be?
Well, if the magnetism came from electrons orbiting the nucleus like little current loops, you'd expect a certain value for this ratio, often called G, roughly 1. But for iron, the measured value is almost exactly 2. And G2 is the definitive signature of magnetism coming purely from electron spin. Orbital motion would give G1. So this experiment nails it. Ferromagnetism is overwhelmingly due to electron spin.
That's really compelling evidence. Okay, but then, if iron has this built-in spontaneous magnetization, why isn't every random chunk of iron, like a nail or a paperclip, a super strong magnet already?
Right, that seems like a paradox, doesn't it? The answer is magnetic domains.
Domains?
Yeah, the material, even though it wants to be magnetized internally, finds it energetically cheaper overall to break itself up into lots of tiny regions called domains.
Okay.
Within each tiny domain, yes, all the spins are perfectly aligned. Spontaneous magnetization is happening locally, but the direction of that magnetization points a different way in each domain.
Ah, so they cancel each other out.
Exactly. One domain points north, the neighbor points east, another south. On average, across the whole piece of material, the net magnetization is 0, or close to it.
Why does it do that? Why split up?
It's all about minimizing energy. A single, uniformly magnetized block of iron would create a really strong magnetic field extending outside the material. Storing energy in that external field costs a lot.
Right, fields have energy.
By splitting into domains whose fields internally loop back or cancel externally, the material drastically reduces that external field energy. So the unmagnetized state, with all these domains, is actually the lowest energy configuration for the whole chunk.
Makes sense. And what's physically between these domains? Is it a sharp line?
Not quite sharp. There's a transition region called a domain wall, or sometimes a block wall. It's maybe 100 or so atoms thick.
So a gradual transition.
Yeah, across that wall, the direction of the electron spins slowly rotates from the orientation of one domain to the orientation of the next. The wall's thickness is actually a compromise between different energy costs.
Okay, so if the domains are already there, when we bring an external magnet near a piece of iron, what happens? We're not creating the magnetism from scratch.
Precisely. You're manipulating the domains that already exist. When you apply an external magnetic field, H, the domains that happen to be aligned or mostly aligned with your field start to grow.
They grow. How?
The domain walls move. Walls separating a favorably aligned domain from an unfavorably aligned one will shift, making the favorable domain bigger and the unfavorable one smaller.
And is this movement smooth?
No, generally not. This is key. The walls tend to get snagged on imperfections in the crystal lattice, impurities, stress points, grain boundaries.
So they jump.
They jump. They move in little jerky steps. They'll be pinned. Then the external field gets strong enough and snap. The wall suddenly jumps to a new position.
And those jumps, can you actually detect them?
You can. This is called the Barkhausen effect. Those sudden, irreversible jumps of the domain walls cause tiny, abrupt changes in the overall magnetization. If you wrap a coil around the iron and connect it to an amplifier and a speaker,
You can hear clicks.
you can literally hear clicks or a rushing noise as the walls jump past those pinning sites. It's direct evidence of this jerky, microscopic domain wall motion. And importantly, it shows energy is being lost in the process.
That energy loss, that sounds like it leads directly to hysteresis.
Exactly. Hysteresis is the macroscopic consequence of all those irreversible domain wall jumps. It means lagging behind.
Right, the famous loop graph. Can you describe what that represents?
Sure. Imagine you start with unmagnetized iron, H 0, B 0, 0. You gradually increase the external field H. The magnetization B increases as domains align and grow, but not linearly because of those jumps. Then you decrease H back to 0. Does B go back to 0? No. Because some of those wall movements were irreversible, some domains stay aligned. You're left with a residual field BR. The iron is now a permanent magnet. Sort of.
You have to force it back to 0.
Right. You actually have to apply a magnetic field in the opposite direction, a negative H, to make the magnetization B drop back to 0. The strength of that reverse field needed is called the coercive force, HC.
And if you keep cycling H back and forth, B traces out that characteristic loop shape?
Yes, the hysteresis loop. And the area inside that loop represents the energy lost as heat in the material during each cycle due to those irreversible domain wall movements.
Which brings us straight to practical materials. The shape of that loop basically defines whether a material is good for, say, a transformer or a permanent magnet.
Absolutely. You engineer the material to get the loop shape you want. For soft magnetic materials, like the silicon steel and transformer cores, you want magnetization to follow H very easily with minimal energy loss.
So a narrow loop.
Exactly. Very narrow loop. Low residual field BUR and very low coercive force HC. You want it easy to magnetize and demagnetize with every AC cycle, losing as little energy as possible.
And for permanent magnets, the opposite, I
The
assume.
complete opposites. For hard magnetic materials like Alnico V or neodymium magnets, you want them to stay magnetized once you've done it. So you want a huge residual field BR and an enormous coercive force HC.
A really fat hysteresis loop.
A very fat loop. You deliberately introduce things into the material precipitates, stresses that pin those domain walls really strongly, making it incredibly hard for them to move back once aligned. They lock the magnetization in place.
It's amazing how much materials science goes into just tweaking that loop. And the chapter also points out how fundamental crystal structure plays a role, like in iron.
Oh, definitely. Iron has this body-centered cubic crystal structure. And it turns out it's much easier to magnetize a single crystal of iron along certain directions than others. It's anisotropic.
Which directions are easiest?
The easiest direction is along the cube edges, the 100 direction in crystallographic terms. It takes more magnetic field energy to saturate it along the face diagonals 110 and even more along the main body diagonals 111.
So the crystal lattice itself guides the magnetism.
It does. The exchange interaction energy and other magnetic energies depend on the direction relative to the crystal axis. Interestingly, ordinary polycrystalline iron, like in a nail, is often easier to magnetize than a perfect single crystal.
Why is that?
Because in polycrystalline material, you have lots of tiny crystals, randomly oriented. So whatever direction you apply the field, there are always some crystals oriented favorably, providing easy paths for domain growth initially.
Huh. Okay, we've covered ferromagnetism pretty thoroughly, iron, nickel, cobalt. But the chapter also briefly mentions other, more complex magnetic orders, right?
Yes, it touches on situations where things aren't just simple parallel alignment. You can have antiferromagnetism. In antiferromagnets, the exchange interaction actually makes neighboring spins want to align antiparallel. Up, down, up, down.
So they'd completely cancel out no net magnetism.
Exactly. On a macroscopic scale, there's no net magnetic moment, at least above a certain critical temperature called the Néel temperature. Manganese oxide is a classic example.
Okay, and then there's also ferromagnetism. How is that different?
Ferromagnetism is kind of a mix. Like antiferromagnets, neighboring spins point in opposite directions. But crucially, the magnetic moments on the alternating sites are unequal in strength.
Ah, so the cancellation isn't perfect.
Right. Maybe the upspins are stronger than the downspins or vice versa. So you still get a net spontaneous magnetization, but it's generally weaker than in a pure ferromagnet where everything lines up parallel. The classic examples are ferrites, like magnetite, the original lodestone.
Ferrites. Why are they so important technologically?
The big advantage of many ferrites is that they are electrical insulators, or at best, semiconductors.
Unlike iron, which conducts electricity very well.
Precisely. If you try to use a conducting ferromagnet like iron in a high-frequency device, like in microwave circuits or radio antennas, the rapidly changing magnetic fields induce strong electrical currents within the iron itself, eddy currents.
Which just waste energy as heat.
Massive amounts of energy. Ferrites, being insulators, don't suffer from these eddy current losses nearly as much, so you can use their magnetic properties at very high frequencies where metallic magnets would be useless. They're vital for things like microwave circulators, inductors, and antenna cores.
So we've journeyed from this weird quantum exchange force dictating spin alignment, seen its thermodynamic signature, figured out domains in walls, explained why iron isn't always magnetic, understood hysteresis, and now landed on these specialized insulating magnets for high tech. That's quite a path.
It really is. It shows how the seemingly simple phenomenon, magnetism, relies on this incredibly deep interplay between quantum mechanics, thermodynamics, and material structure, from electron spin to practical devices.
And it highlights that even fundamental concepts can have layers of complexity we're still figuring out.
Absolutely. Especially around those phase transitions like the Curie point. The detailed physics can get incredibly complex and is still an area of active research. We don't have all the answers, even for these simple magnetic materials.
Okay, let's leave our listeners with a final thought, something pulled right from Feynman's chapter. We've spent this time understanding the sophisticated quantum basis for engineered magnetic materials. Yet, the chapter ends by noting that lodestone, magnetite, the first natural magnet known to humanity, is still puzzling.
Hmm.
Why don't we have a completely clear picture of how lodestone gets naturally magnetized in the Earth? Or, for that matter, a full understanding of the mechanism generating Earth's own magnetic field, the dynamo theory. It's a good reminder that nature still holds some magnetic mysteries. Something for you to ponder. That's it for this deep dive. We hope this exploration into magnetic materials gave you some fascinating new insights. Thanks for learning with us.